So the next question we want to answer, and it's really a fundamental one from a research perspective. If I want to be able to estimate the population parameter with a given level of accuracy, what sample size do I need to accomplish that? What value for n in the margin of error formula is going to give me that required level? Right. Okay, so this is actually simple enough to do. I've got my margin of error formula here, and it's solved for e naturally enough, but I want it to be solved for n. I want to know n equals something, right? I want a formula for n. So all I'm going to do is solve this. I'm going to divide both sides by z alpha over 2, move that over to the right side, to the left side. Now I'm going to square both sides. P hat q hat over n equals e z alpha over 2 squared. Right, then let's see, multiply both sides by n. P hat q hat equals this e z alpha over 2 squared times n, and then divide. Right, divide by this squared part here on the right. N equals p hat q hat z alpha over 2 divided by e squared. And there you go. Right? That's it. That's my formula. Right? That's my formula for calculating the minimum required sample size to get a given level of confidence. All right, so let's see how we can use this, right? I've got a question here. You're conducting a survey, and you want to estimate the percentage of voters in favor of your candidate. And I want to know what minimum sample size do you need to be 95% confident that your result is within 2 percentage points of the population. All right, well, first, let me just write my formula here. N equals, let's see, this was P hat Q hat Z alpha over 2 divided by E squared. And we've got a problem. I know what E is. E is my margin of error. It's 2 percentage points. So E is going to be 0.02. And let's see, my confidence level is 95%, and the corresponding critical value, you can calculate it, you can get it from your table, however you like. This is 1.96. So that's great, but P hat and Q hat, I don't know. Right? And how can I know them? P hat and Q hat come from the sample. I don't have the sample yet. That's the whole point. Right? I need to know how many people I need to survey to get my sample. Well, this does happen. Right? This does happen. And what we'll often do, we'll do an estimate when you truly just don't have values for P hat and Q hat. We'll let P hat Q hat equal 0.25. And that's usually a pretty decent estimate. So if I put these numbers into my formula here, this is 0.25 times 1.96 divided by 0.02 squared. My calculator tells me this is 2,401. Okay, came out even, which was nice for me. Okay, but let me make a point here, right? We need to talk about rounding. If you get a decimal value, what should you do? Well, this is a case where you always round your result up. If you round up, your eventual confidence level will be a fraction over what you wanted, and that's fine. If you round down, even by just a little bit, your final confidence level will be slightly less than what you wanted, and that's not okay. Right? So you are always going to round the sample size up. Okay, so take a look at this thing. We've got another situation here. I'm working the same election example again. We want to be 95% confident. Our margin of error is 2 percentage points. But this time, we did this research last year. Last election season, maybe. right? And I know that that my candidate carries 62% of the vote. Okay, well, if I have historical data, this is another option that I can use for my p hat, right? So I'm going to do z alpha over 2. That's still going to be 1.96. Our confidence level is still 95%. Our margin of error is still 0.02. And now I'm going to use 0.62 for p hat, which means q hat is 1 minus 0.62, or 0.38. And now I can go to my formula, right? N is z alpha over 2 over e squared p hat q hat. So this is 1.96 divided by 0.02 squared times 0.62 times 0.38. And I'm going to go to my calculator. And I get 2262.7, which I'm going to round up to 2263. There is my required sample size. Okay, so one point I want to make about this before we move on. Remember, I'm not saying in a situation like this that you would have to call 2,263 people. You don't need to make 2,263 calls. You need that many responses, and a lot of people aren't going to answer. They're going to hang up, right? So in a practical research scenario, right? Remember, you need to plan on actually calling significantly more than that to get that number of actual responses. Okay, so I want you to go back and look at that formula again. And I want you to notice something about it. The size of the population doesn't figure into the formula. Right? In the last question, we need to survey 2,263 people. Doesn't matter if the population has 5,000 people or 500,000. 2,263 people will give us the right result, the confidence level that we're looking for, either way. Okay, and that if you think this through, it makes sense. Why do we need a certain sample size? Well, it's not to make sure that our sample is representative. Well, it is kind of to make sure our sample is representative. But we took care of that by making sure that we're sampling from all strata and that we're not only doing wealthy people or rural people or whatever. We've already got that covered. Right? The reason we pick a minimum sample size is purely to make sure that the probability of our accidentally getting a bizarrely skewed sample, because they are out there, is minimized. Right? That is the only reason we're picking a minimum sample size, and that's why it does not in any way depend on the size of the actual population. Okay. That's confidence intervals for a proportion, right? Our next step is to talk about another parameter. We're going to talk about how you can find a confidence interval for the mean of a population. And to do that, we're not going to be able to use our old friend, the normal distribution. We're going to have to introduce a new distribution called the student's t distribution.